Hi, my name is George Paris, and I hope to complete my series today of the thermodynamics. I, if you've been following this is the fourth of four videos that are based on a book which I wrote. The first video has to do with heat and heat capacity. The second video has to do with uh, entropy, enthalpy, and free energy. Sort of a classical workup of that. The third one is statistical thermodynamics based on Boltzmann and Planck's work. And this video is basically a derivation of a couple of equations which occur in all the textbooks having to do with rates and equilibria. In particular, we're going to develop the Arrhenius equation here. So here we go. This is the book that I'm talking about. This is published on Amazon.com. You can buy it it's a paperback. You can buy it for $6.38, it looks like. There's a Kindle version as well. The videos are self-sufficient. The book is self-sufficient. So it doesn't matter which one or both that you look at. The book does have some material that I've skipped over in the videos because it just sort of it's an add-on. It's sort of it goes into more detail than perhaps the average student would be interested in. In particular, it relates to as we approach absolute zero, you get some effects that have to do with like superconductivity and stuff like that we don't need to talk about in the basic video here. So if you're interested in superconductivity and things that happen below, say, 15 degrees Kelvin, you need to go look at the book, but otherwise you can just breeze through here. All right, now, first thing I want to talk about is the relationship between delta G and the equilibrium constant. Okay, that's delta G and KEQ. I have selected a particular stoichiometry to look at here in which I have hypothetical molecules A in equilibrium with 2B. Okay, this is some sort of a dissociation in equilibrium, but you know, it's selected for a particular reason. Not only do I want to show the basic derivation, but the reason I've selected this particular system is because it will allow me to go and talk about another step beyond the basic equilibrium. So here, let's go with this. I've expanded it to, if you look at the graph on the right here, I have expanded the equation to capture several distinct steps, energetic steps. Yeah, first off, if B and B are going to react to form A, they obviously have to get together. And this would be like if you're talking a gas phase, we're talking like a collision complex, or if you're talking in solution phase, we're talking about like a solvent caged pair or something like that. And then there's a transition state, TS, and I use this double dagger symbol to make sure you're thinking about the transition state. And then, of course, you have A and you have the 2B, B plus B. All right, so going forward from here, what we're going to do is we're going to use the Maxwell-Boltzmann equation. I've talked about this, I think, in every part. It's a very useful equation. Very underlies a lot of thermodynamics, both classical and statistical. And what we're going to look at here, go back to this. The N, the capital N in this equation, that's the thing in the golden box up there, is going to represent the number of particles. And you can have the number of particles in the ith energy level and the number of particles in the ground state, that'd be N0. And that's going to equal to the ratio of the degeneracies, Gi over G0. For purposes that I use here, we're just going to call that ratio unity 1 because we don't have any basis for getting involved and figure out what the multiplicity of states that you would have in Gi or multiplicity is G0. So we're just going to call that ratio Gi over G0 is going to be unity throughout. And what you're left with is the exponential term, which is the change in energy between the two energy states, and the thermal energy, Kb, times the absolute temperature. So going from there, plugging into that equation for the forward reaction, what we have is the exponential term, that ratio for the A in the activated state. This is the forward reaction, and A in the ground state is going to equal to this exponential term, which is the energy of activation for the forward reaction. That would be the difference between A and TS. That would be the transition state. And then for the reverse reaction, we've got to consider both of these because we're looking at equilibrium. You've got the same thing with BB, and in this case, I'm looking at the B:B. That would be the solvent cage material, whatnot. And the activation state going to transition there. Similar equation. Now note that in this first case, I've just as a matter of the way I set the project up, the BB, that would be the separate B plus B, is at the same energy as the BB. I mean, there's this only thing that's driving this is statistics. It doesn't have anything to do with energy, and so that these things are on the same energy levels. Keep that in mind. This in the first case we're looking at here. Okay, now at equilibrium, the number of molecules at the transition state that are headed from left to right, that would be the forward reaction, must equal the number of molecules that are going from right to left. That would be the reverse reaction. That's what this NA double dagger is equal to NBB double dagger is equal. Now, once you set that up, you can go back over and take those, rearrange those two equations to the left of that, and then set them equal once you've got the, what you solve for NAA double dagger, or NA double dagger and NBB double dagger. Set those two things equal, take a ratio, and go for what you got there, and you end up with this ratio of the energy terms, the exponential terms. Do some algebra on that, combine the exponents, and then basically be explicit about what the delta G BB is and delta GA is, and basically the G double dagger just means that's the energy of the transition state. So once I've done that, I can actually get rid of the energy of the transition state. It subtracts out. And then recalling that the energy of these two states are equal, we now can go forward, and we have the NBB over NA. That would be the difference between the energy of the number of atoms in A and number of atoms in BB. And that's going to be related to their energy of activation, or the reaction energy, delta G for the reaction, divided by RT, negative of that, exponential. And the question arises, how can I relate these numbers of molecules or numbers of atoms to something analytical, or something that I can actually measure in the laboratory? Well, we don't know what the probabilities are for NBB or NA, but we know that the relative probabilities should be proportional to the numbers. And so the ratio of the numbers should be equal to the ratio of the probabilities. That's what I have here at the lower right hand corner of this equation. And then once we've done that, we understand that the ratio of the probabilities are going to be proportional to the ratios of concentration, which is straightforward. And so I can use the ratios of concentrations as a surrogate for the ratios of probabilities. So I'm not actually using the concentrations, but I'm using them as a surrogate for the probabilities. Plug that in, and keep in mind that those probabilities are pure numbers. They're not. There's no units to them. And so this is going to get to one of those questions, the nagging questions that students always ask. Well, why don't equilibrium constants have units? Like I did the arithmetic, where did the units go from? And the reason that we don't worry about the units is because as long as everything is measured in the same unit, all we're really looking at is the probabilities, which are unitless. They're pure numbers. So that solves one of the classic questions that a smart first-year student will ask you about kinetics. But here we go. So this dimensionless ratio is equal to the equilibrium constant. Okay. Now, once we've done that, we can start rearranging and solving for delta G. And that's, take this ratio and then take the log through here, and then we go back and we rearrange that, and we end up with delta G for the reaction is equal to the minus RT times the natural log of the equilibrium constant, which is a pure number. And so this I think probably occurs in most general chemistry textbooks today, but exactly how we got there is usually pretty vague. But it's a direct result of the use of the Maxwell-Boltzmann equation. Okay, I'm going to take this another step. And we're going to say, okay, this is why I did this unusual stoichiometry for this reaction. Suppose, unlike the first case where the B plus B and BB had the same energy, now let's say that they don't have the same energy. There's a difference in energy. And now I've got to deal with that. How do I deal with that? Well, basically there's an energy involved in this. There's an equilibrium between B plus B and B colon B. Okay, there's a pre-equilibrium that goes on here in the reverse reaction, and we have to take consideration of that, because I'm going to talk about the thermodynamic concentrations, the thermodynamic numbers here versus the analytical concentrations. The analytical concentrations, if I go and take a sample of this solution and analyze it for B, I can't separate the B's that are by themselves and the B's that are part of this collision complex. All right. So analytically, I can't distinguish those two, but I need to correct for the fact that they're not at the same energy and that there's a separate equilibrium involved here. And I'm going to do that fairly straightforwardly. I got introduced to this in a very awkward way. I was working for Dr. G.G. Long down at NC State. Actually, I was on active duty with the Army, but it was easy for me to commute home on weekends, and I had a few weekends I could do that. And that was in 1972. And I collected data using conductance measurements for a reaction that Barbara Andrews, one of the graduate students of Dr. Long, had generated. And Barbara had realized that when we made one of the many compounds we made was triphenylmethylstibonium bromide. And Barbara realized that she took this nice crystalline compound, dissolved it in acetonitrile, and it started decomposing. And she detected methyl bromide, NMR, and all that kind of stuff. And so, realizing that we had this reaction going on, and we had conductance equipment there, and I started following it. I generated a bunch of conductance, changes in conductance as a function of concentration. And that happened like in 72. It took me like 3 years before I figured out what was going on. It did not follow a typical second order rate equation, which is what you'd expect. And that was a result of a couple of factors. One, you form ion pairs, which are effectively neutral. And then you have these ions kicking around in a fairly polar solvent. And what that does is it changes the activity coefficients. And so when I got through sorting through all this data, I was able to separate out the association constant alpha. And I was also able to calculate using the Debye-Huckel equation, which I'll introduce in a moment. I was able to calculate the activity coefficients, these gammas. And once you plugged all that into this equation, you got pretty good kinetics. And so this was a very interesting experiment. And I ended up, like I said, it took me about 3 years to figure it out, but it was worth the time. R.M. Paris was my wife at the time, and she and I consulted on this project. She put up with me going into the lab on Saturdays when I was in the Army instead of hanging out with her. So we also talked about it a bit. So here we go. The only reason the collision complex would not be statistical is because there's some force driving them together or driving them apart. And we have to take consideration of that. And then when the ions are strongly polar, or you have ions, you can use the Debye-Huckel equation to calculate these activity coefficients. The analytical equilibrium constant and what I call the thermodynamic equilibrium constant are different because of these activity coefficients. And the activity coefficients effectively are equilibrium constants that relate the two together. Now you can calculate those activity coefficients, as I said, using the Debye-Huckel approach. And unless you're dealing with ions, these activity coefficients are not necessarily going to be very different. If you just have nonpolar, uncharged molecules, you probably will not see a drastic difference that causes this problem. But if you do get, if you're dealing with ions, you do have to worry about ionic strength and changes of the ionic strength as the process goes along. There's a classic equation that we do in as an undergraduate, this so-called clock reaction. Now, if you go through there and start figuring out they have a recipe that you mix things together to get the two reagents that you mix together to do the clock reaction. If you do the arithmetic and you realize what's going on, what they're doing, they're putting, because they're changing the concentration of the active agents, they need to keep the concentration of ions constant. And so the reason this recipe changes is because they're keeping the concentration of ions constant so the ionic strength doesn't change. Because if you change the ionic strength, that's going to change the activity coefficients, and the poor undergraduate students who do that experiment would not be able to fit it to a second order or whatever the order of reaction it would be, because you'd have very strange looking equations, very strange looking results from that experiment if you did not keep the ion strengths constant through that process. So anyway, this is the I here in this equation is ion strength, and you can use that to calculate the activity coefficients. And that is the case where you're most likely to see this discrepancy. Now let's go back and look at the Arrhenius equation. We've already done most of the heavy lifting in terms of looking at the equilibrium equation, because the rate equation is roughly half of the equilibrium equation. So we go back and look at our system here. Now, there's a couple of different terminologies. I use them sort of interchangeably. I talk about activated complexes. I talk about transition states. I think the organic chemists typically use transition state, and I think the people doing gas phase work typically talk about activated complex, but they're conceptually the same thing, and I use the two terms pretty much interchangeably. So once you get to that state, once you get to the transition state, you're about to, you have all the energy you need and all the pieces you need to go forward. And the question is, how fast can that happen? And so basically you're talking about changes in bond lengths and bond angles and that sort of thing as you go through here. And so the molecule cannot fall apart faster than it vibrates because you're talking about these individual pieces, either individual atoms or individual pieces of, like two or three atom cluster going flying off some part of the molecule. And so you have to look at the vibrations of the molecule, and that should determine how fast the activated complex falls apart to the products. All right. Now, once you can calculate the concentration or the number of molecules that are in this activated state using the Boltzmann equation again. And then once you've got that, you just have to multiply it by this frequency factor. That's up there at the top right of the equation. The frequency factor, like I said, should be on the order of magnitude of the vibrational frequencies. That is, if that's what is limiting the rate of reaction. And that would be typically 10 to the 12th or 10 to the 14th per second for typical vibrations that fall in the infrared spectral range from like 500 to 4,000 reciprocal centimeters. Now, if you experimentally find something that's much higher, it's hard to rationalize a higher frequency unless you're looking at either some combination of vibrations, which would be like near infrared stuff, or straight up electronic transition. If you have an activity coefficient, not activity, but a frequency factor that comes out looking like, say, 10 to the 20th, you're probably looking at a electronic transition, not a molecular transition, because it is a much faster process. On the other hand, if you end up with a frequency factor that is much lower, then it sort of implies that there's something, not only do these two pieces have to come together or get in a position to go apart, but they have to be in a very special arrangement to do that. So there's another twist to this process. It's just not randomly together. So this sort of implies that there should be another factor. It could be another factor in there. And let's look at this for a moment. Let's go back and see how this reaction relates to the rate equation. Once I've got this equation for the activation complex, just basically the equilibrium, if I plug in the activation, that vibrational frequency number that is shown here, it's Arrhenius' factor, it's the capital A double dagger, and I compare that to the rate equation where I've got a rate constant and I've got the concentration. You see that the rate constant is going to be that first, it's the exponential factor, and it's also that frequency factor. So the rate constant is typically the frequency factor times this exponential term. And that's the classic Arrhenius equation. Now you can carry this another step further and start to say, okay, well, I want to take care of the possibility that there's some unique conformation of this molecule that's going to have a big impact on the rate. And so I'll do that by, instead of looking at the free energy, delta G, I'll look at as a single term. I'll break that down into a delta H, which I can equate to the energy of activation, and the delta S of activation. And so I'll plug in, for delta G, I'll plug in delta H of A and delta S of A, and do the arithmetic. And at the bottom here, I have a new equation where I've got the two things in red are the two things I've added. One is the frequency factor, the Arrhenius frequency factor, A double dagger. And the second part is this delta S of activation that has to be considered. Now, once I have put those two things through here, I'll go to the next page. I can call it that entropy of activation. I could call it. I think this is that a rho? What is that? Rho star. So I've got these two terms. I have the frequency factor A, and then I have this Greek letter. I think it's rho star. And back to my energy of activation again. Now I can use that equation, but that's not a linear equation. It's got some exponential thing. So to linearize that, I will take the log through both sides of that. So the natural log of the K rate, which I can measure experimentally, is going to be the natural log of this two factors that are multiplied together, the frequency factor and this orientation factor, or this entropy factor, and minus E sub A over RT, the energy of activation. So if I do that arithmetic, I can now I've got a linear equation I can plot, and I've got on the right hand side here, what I'm going to do is plot the natural log of the rate constant versus 1 over T, and this is sort of a typical equation here, typical slope, 2 or 3 points in a straight line, and the slope is going to be minus E sub A over RT. You'll notice a negative slope, minus E sub A over R, and that's the slope. And then the intercept is going to be natural log of this two factors that are multiplied together. This actually comes from a fairly recent experiment I did, and if you put that all through, you're going to find out that it's got a very high frequency factor, like 10 to the 20th or something like that. I concluded that it was a electronic transition that led to the reaction. So that's sort of where we're at. I appreciate your time. I hope this last video has been mainly a couple of derivations that primarily exercise in algebra, and hope you've gotten something out of it. My goal through this whole series is to demystify thermodynamics. I don't think it's as big a mystery as everybody ends up thinking it is once they get out of the typical classes. I'll reiterate my opinion that the engineering people, starting with Carnot and Joule and Watt, who were only interested in making money through steam engines and whatnot, and we're using the caloric theory of Lavoisier, they basically got everybody off of one track, and we focus on that. The engineers are still out there. As molecular scientists, chemists, biologists, and molecular biologists like that, I think we have gone past that in terms of understanding what's going on in thermodynamics. And in fact, Boltzmann has sort of dragged us into that, kicking and screaming. And so I hope that I have clarified some of the origins of some of these terms and why they work. I think we teach students to be practitioners. They can take the equations, take the data out of the table, plug it in, do the arithmetic, and come up with answers, which most of them never use. But understanding what's going on is a whole different kettle of fish. I think most people, if they were honest, most people teaching freshman chemistry today, if they were honest, would say, I really don't understand what entropy is. It has something to do with disorder, but it's like they don't understand the roots of it. And they don't understand how Clausius and Boltzmann can be true at the same time. In any event, there we are, and I hope I can publish this on YouTube, and you will have access to it. The book, I would highly recommend the book. Obviously, I wrote it. So y'all have a great day.